Good afternoon stroke evening. My name is Dan, and today I'm going to be talking a little bit following on from my previous talk that I did for AstroSoc a couple of days ago into methods of detecting dark matter that look towards the sky, looking at a lot of theoretical models of dark matter and how we could really go looking for it out in space. So let's go on another little journey. So to kind of summarize what we're going to be doing today on our little adventure, I'm going to start off again with a couple of introductions. This might come across as kind of the same as the previous slides that I did a couple of days ago, and if it does, that's because they are. So if you've watched before, you can feel free to skip a couple of slides ahead there. But I felt it best to introduce myself so this becomes kind of a self-contained thing anyway. After that, I'm going to be going over a couple of dark matter candidates in some detail and kind of talking about how we design our specific models for dark matter candidates outside of just it has a mass and it doesn't emit light, which is kind of a spoiler for in a second actually. After that, I'll be going through a couple of experiments with acronyms like CAST and LSST and AMS and LIGO, and at least one of those is something you're probably familiar with by this point as an astrophysics society. But all of them have their own place in detecting dark matter. Each of them have a different method of doing so, and I'll be going over a little bit of detail about each of these. So with that being said, let's just get started. But before I get started, just a little, we're going to put the brakes on real quick here. A physics alert. There will be physics in this talk, and it's going to be particle physics, which I understand and you don't. And there's going to be some astrophysics, which some of you will understand and I don't. So we're really going to have to kind of help each other out on this journey that we're going to go through here. Unlike the previous presentation that I did a couple of days ago, I won't be using this as a warning through the slides. For better or for worse, we're going to have to get into quite a lot of theoretical physics sections through parts of this talk, especially at the very beginning, and that didn't really allow a position to put this in a lot of the slides. So I'm sorry about that in advance, and I'm also sorry about the fact that we're going to have to be talking about physics. I know it's for nerds. I am one. Let's just get going and pretend that's not the case. But who is this person who's telling you that they're a nerd and that you should pay attention to them anyway, and why should you care? So who am I? My name, as I said before, is Daniel Hunt. I prefer Dan, but I figure it's more formal to put Daniel on the slides. This is me at an AstroSoc event about a year ago, presenting a talk on, who'd have thought, dark matter. Kind of got me into the PhD that I'm doing today, but to learn more about that, you can go to my talk from a couple of days ago. I'm a former master's student at the University of Birmingham, and I'm currently working on a PhD on the LZ experiment, a direct dark matter detector on the ground at Oxford. Again, I talked about this a couple of days ago. I'd really recommend that video. I also, again, I really like to say this one, won the esteemed Poynting Physical Society Award of Big Name in Physics in 2019, though I was woefully disqualified in 2020, as you're apparently not allowed to win the award twice, though I plan on bending that rule by being the first person to technically win it 3 times in a row, so watch this space. And in the first year of my undergrad, I learned all about dark matter and kind of the holes in the standard model of physics that we know and somewhat love today, and how those kind of holes in the standard model can really be solved by dark matter. But we'll get to that in a second. So what is dark matter? Yada yada yada. I've already done a talk on this a couple of days ago. I'll direct you towards that if you're interested in knowing some of the specific details. But basically, we found that areas of galaxies were rotating faster than they should, as if there's a mass around the outside of them that's causing them to spin faster. And we found that light is bending around certain galaxies more than it should, implying that there's more mass there that we can actually see. So that and a bunch of other evidence seems to imply there's a great big chunk of something out there that is unable to be seen by our telescopes and stuff like that, because we rely on electromagnetism a whole awful lot when it comes to seeing things out there. But we rely on that and we can't actually see whatever this mass is. So there's invisible mass out there. There's dark mass, this dark matter. And with that, we get to a couple of interesting conclusions. You come up and you say, aha, this thing has mass. We also can't see it, which means that it doesn't emit light, which means that it isn't affected by electromagnetism, which means it doesn't have a charge. I'll give you that one for free. We know that it doesn't decay much, or we'd see the decays and we'd be like, hang on, that's something we should look at, though some of that we'll get into during this talk today. That does mean, though, that we set an upper limit on what we call the coupling to the weak interaction, just a nuclear force. So it's not very nuclear, let's just say, though I know a lot of people would be angry at me for saying that. But we have kind of a picture as to the general specifics of what we need when making these dark matter candidates here. So let's keep on going and think about what other parts of the standard model could imply that dark matter is a thing. So before I keep on going, I should probably explain what the standard model is and why it kind of motivates a lot of our dark matter models. So the standard model is all of the physics that we know more or less up to around 2012. So you've got a bunch of quarks that make up protons and neutrons. You've got a bunch of leptons, like electrons, and a couple of heavier versions of the electron, the muon and the tau. You've got a bunch of neutrinos, which are these massless, or not massless anymore, that's one of the problems with the model, blips of light that are just going through space, don't interact with anything, barely do anything, which is part of the reason we don't know much about them. And then you've got the force particles, so stuff to do with the weak interaction, which is the nuclear force, the strong interaction, which glues protons together, the electromagnetic force, photons, or light, as you probably are more likely to know it, and gravity, which is one of the problems with the standard model, being that we don't know what motivates gravity as a force. That one isn't mentioned on the slides, but it's one I'll throw in for free. But that aside, there's a couple of problems with the standard model. The first of which is, what the heck is the Higgs? We know that it's a thing. It explains a lot of problems in the standard model about why things have the mass that they do, why there's two particles in the weak interaction and in the electromagnetic force that more or less behave the same, but one of them is massless, light, and the other one has a mass of around 100 GeV, the Z boson. So what's going on with that? And the Higgs comes along and it explains some of these things in a process called symmetry breaking. These two forces, because of the Higgs, influence the world in slightly different ways. But there's still a lot of questions to do with the Higgs, because it behaves in a way unlike anything else that we know. It's a completely different type of what we'd call a boson, a force carrier. And it's got a whole other bunch of physics attached to it, namely the fact that it's capable of permeating space. No matter how far away you were to get from the Higgs, it would be there and it would be able to influence you, as opposed to electromagnetism, where, get far away enough from a fridge magnet and it won't really affect you that much. So there's a lot of questions to do with the Higgs that we need to answer when doing physics in the next decade or so, There's also the problem that up to this point we've only reached around 13 TeV. That's tera electron volts. The best comparison there is that the proton has a mass of around 1 GeV. But regardless of these energy scales, we've only got to a certain amount of energy. But that means we don't know what happens at these higher energies, where we can make heavier and heavier stuff by smashing protons together faster and faster. So what if we find something at these higher energies that just doesn't match with what we currently know about the standard model? What if something else comes along that's just way heavier and we just couldn't find it because of that before? But these are quite small problems, right? These are just things that we need to poke with a stick a little bit more. But there's actually larger problems with the standard model. One of these is the hierarchy problem. I mentioned neutrinos before, and the fact that we have different types of neutrino, little massless blips that we now know have mass. And the problem with that is that we only recently worked out that they have mass. We did it by proving that there was some weird quantum effects where they could oscillate into each other. It's a whole kettle of fish separate to this talk. But the problem with that is that as soon as you know that they have masses, the question becomes which one of these particles is the heaviest. And that's where the hierarchy problem comes in. Not only that question of which is the heaviest neutrino, but also the question of how some other particles have different masses from each other and how they stack up against each other. And can we explain this with any other kind of matter that's influencing them in the same way that we managed to explain the weak interaction and the electromagnetic force using the Higgs? Is something like that out there? As a much bigger problem is this thing called charge symmetry. Now, This is again a very complicated subject, arguably one that I'm not qualified to discuss. But for all intents and purposes, C-symmetry is the idea that if you were to reverse the charge of everything in the universe, like positive becomes negative, negative becomes positive, the universe should behave more or less the same, just kind of a mirror image of itself, but it should still work. And we found that certain interactions and decays, specifically to do with cosmic rays called kaons, didn't follow this C-symmetry. So we say, right, what if we flip the charge of the universe and flip X and Y? So we kind of literally make a mirror image with inverted charge as well. If we do that, would this make sense? Would this symmetry breaking we see here make sense? Would this difference between producing particles and antiparticles make sense? And the answer is no, because there were more kaon decays found after this, more problems with CP symmetry, as we call it, charge parity. And this is something that the standard model isn't really built to answer. We're hoping that by doing some research into kaon physics with an experiment such as LHCb or Na62, and doing some detection work with neutrino experiments like IceCube and SNO, we can look into a little bit more detail about these charge and parity problems. But up to now, it's one of the gaping, great big problems with particle physics. And it also fits into a cosmological problem as well, which is, why is there more matter than antimatter in the universe? Why was there this weird slight imbalance towards matter that means that we're now here and I'm standing here in front of this desk, in front of this microphone? How did that happen? Then there's the big problem, which is just an entire other kettle of fish here, which is that we know that baryonic matter, or the matter that I've talked about here, is about 5% of the universe, with around 25% being dark matter and then another 70 or so % being dark energy, which we're still not going to talk about in this talk too much, because that's for a more qualified cosmologist to talk about. But it's still clear that we only know about this very specific portion of the universe. So there's a fair few problems with the way the standard model works. And that's good to an extent, because it means that people like me can keep on being paid. But it leaves a lot of work to be done. So we've done well. There's a bit of stuff to work on. The standard model's still okay, but there's still some things we have to develop. So we've got a couple of issues here. And we can solve these a little bit. We can, for example, look into a lot of stuff to do with the Higgs by talking about it as this Higgs portal. If we can reach the point where we can produce the Higgs boson on the fly, just reach the kind of energy where you can just reel off a Higgs boson or two as you feel like it, rather than actively searching for it. We've got this thing called the Higgs portal. Specifically, we've produced a Higgs factory. We like our buzzwords in particle physics. But we produce this Higgs portal, this idea that if we can watch the Higgs do different things, it could potentially be our entry point into finding a lot of other weird beyond the standard model physics that only it can produce. But we can get to that at some point. We just need to reach more precise detectors and higher energy accelerators, and we can just start producing the Higgs on the fly. There's a couple of detectors even coming up relatively soon that are proposing to be able to consistently produce the Higgs. We just make higher energy accelerators if we want to reach the high energy physics regime and work out what's going on at those higher energies. The ideas for CERN's next accelerator, either the Future Circular Collider or CLIC, Compact Linear Collider, are two proposals as to how to get to this higher energy at some point or another. The other two here are a bit more difficult, because you can't just build better toys and hope and just assume that something's going to come out of them. With CP symmetry, we go into this aspect of physics called flavor physics. This is something that LHCb and Na62 are hoping to look into at some point soon. Taking precise measurements of these decays which we know violate CP symmetry, and seeing just how much they don't follow the standard model or any of our current predictions. And the hope there, for me at least, is that if we look into that quite a bit, we could suddenly find a dark matter candidate that only really influences these specific interactions, and because of that we don't see it in reality, but it also nice and neatly solves the problems that will be associated with CP symmetry. In the same way, we can hope that by looking into neutrino physics in a little bit more detail, we find some magical force carrier of sorts or something like that, that stops the hierarchy problem from being as much of a problem, that couples specifically to neutrinos and makes them have the mass that they do, and also hopefully we can find out the mass that they actually have in the first place, because that's enough of a problem as is. But if we can, build these detectors and go into these areas of physics coming up, I've pretty much summarized the entirety of the future of particle physics there to an extent. If we do that, we can hopefully find dark matter. Fingers crossed. But then the question becomes, what kinds of dark matter? What are our current predictions? What models fit into these big gaping problems in the standard model? So we'll start with specifically the higher energy regime, heavier particles. Supersymmetry is quite a heavily discussed topic in particle physics at the moment, which we shorten down to SUSY, which sounds really nice. And it essentially says, great, we've got this standard model, which I've finally shown for the first time on the left-hand side here. What if for every single one of these things, there's a slightly heavier and slightly different version that we've only not been able to see because it's a bit heavier? So these are high mass. The mass specifically depends on the specific model of supersymmetry, and there's a lot of debate at the moment about what this could imply. But we're talking at least above the GeV-TeV range. Otherwise, it would need to interact so little that we weren't able to see it during the LHC, which seems a bit unlikely. The properties of the particles, in order to solve a couple of problems within the standard model, say that any half-spin particles become full spin. This is one for the particle physics gang out there that actually understand what I'm talking about there. But for the layperson out there, they behave a little bit differently. Quite a lot differently, actually, but only a little bit in terms of the numbers. They also have very cute names at the moment because we have terrible naming conventions, like the neutrino becomes the sneutrino, or, arguably, according to some people, the neutralino. This is one of the lightest supersymmetric particles. We call them the lightest supersymmetric candidate. And this is potentially one of the first particles we would see as a dark matter candidate as we reach these higher and higher energy accelerators. This solves a bunch of stuff, because as you can tell, we've just designed this based on we've looked at the problems in the standard model and thought, how can we bandage this up and make it still work? How can we plug this hole in the sinking ship that is modern particle physics? So this supersymmetric model would solve the hierarchy problem by coupling to neutrinos. It would solve the CP problem with kaon physics and the weak interaction and all that. And it's just really, really nice. But at the same time, I may have angered a lot of people by talking about this the way that I did. I am not qualified to talk about supersymmetry. We were supposed to have a lecture course this term at Oxford called Introduction to Supersymmetry, and then COVID happened. So I should probably stop here, and I'd recommend looking up a little bit more if you're interested, but at the same time there's a lot of maths going on under the surface here. So we've gone very heavy there. What about something that's light and does very little? Let's talk about the Axion, which actually was called the Axion because of the cleaning brand that you see on the right-hand side here. An Axion is an incredibly light, nearly chargeless, barely interacting particle that's currently predicted to be around the range of 1 milli-electron-volt, so very light, or lighter than anything we've ever seen before. For context, we're having difficulty working out the mass of the neutrinos, and they're 1,000 times heavier than the Axion would potentially be. This also solves CP problems in the strong force, which isn't usually talked about as often when it comes to CP symmetry. So it's a very interesting factoid that it's still an issue. Specifically, observations of atomic nuclei have managed to show us that there's some weird things going on with charge and parity, which, again, I'm not qualified to talk about because I'm not a nuclear physicist. There's a lot of maths going on under the surface here yet again, but as you can tell, both of these models are designed to tie a nice, neat little bow in a lot of the fundamental problems in particle physics. And to give a bit of my own personal perspective for the moment, I think that it's a lot better to search without these specific constraints because it would be a little bit too neat to an extent to expect any dark matter candidate we see to be able to tie up the standard model and patch up these gaping problems in a current perspective of physics. But that's just my opinion, and that's just me going off on a little tangent for a second there. But it's still cool to learn about these models, so what about we find out about a couple more, right? Here's one that I quite enjoy. The heavy neutral lepton. I've had to put a little tau neutrino on the side here because they didn't have... Turns out that for these potential candidates, there aren't many funny pictures. So it's kind of hard to get illustrations for the side of your presentations. So a lepton is anything that isn't influenced by the strong interaction. So it's kind of your electrons, your muons, stuff that isn't bound into the nucleus. And it's heavy because it's a lot heavier than the other leptons we found that exist, and it's neutral, so it's more like a really heavy neutrino than it is kind of an electron. So it's like a neutrino, much heavier. It also solves the neutrino CP problem, as I was saying before. To be more specific on the neutrino CP problem here, we've found that there's certain types of neutrino that are more likely to be produced in the middle of decays. We talk about this in terms of left and right-handedness, and neutrinos and antineutrinos, though all of this is quite difficult to work out because as the neutrino is chargeless, it's hard to compare the particle and the antiparticle, you know? But hopefully this heavier neutrino, this heavier neutral lepton, would interact with neutrinos that we currently see in the standard model, and then we can just kind of tick off the problem of neutrino physics by saying, it's the heavy neutral lepton, that's what did it. Lock him up, throw away the key. However, this would also open up its own entire new can of worms. With a new neutrino that isn't really predicted by the standard model comes a bunch of other theory that we don't really have any models for at the moment. Specifically, we wouldn't know what mass it would be at, just that it would be a lot heavier than most stuff that we see at the moment. And we wouldn't know how many of them there would be. Currently with neutrinos, there's a lot of mathematics that goes on that can prove, and you do it in second year undergraduate lectures, that only 3 generations of neutrino and lepton can exist. Because if you were to go any higher, there would be problems related to quantum mechanics. I forget, if I'm honest. But this maths doesn't actually exist for the heavy neutral lepton, because it doesn't exist at the moment. So a whole other arrangement of maths and a whole other bunch of tests would need to be done related to the heavy neutral lepton, just to see what it does, see what makes it tick, see what keeps it up at night. And we're reaching towards the end of the different candidates here. The dark photon. Now this, I've had to put a picture of a photon here because, again, illustrations are hard to come by. The dark photon is a predicted force particle that we don't see at the moment. It's a dark matter candidate. So the hope is that by finding the dark photon, we can prove that there's an entirely new force out there. And this solves a bunch of problems in particle physics. One in particular that seems to motivate the dark photon from what I've seen is some problems to do with the way that the muon operates, what we call the magnetic moment, so how magnetic it is on different sides of it, and how it orbits. And there's a lot of problems related to that, as well as electrons within atomic orbits that seem to motivate some dark matter candidates out there. But again, we don't know very much about what this dark photon would do, what it would be, what the force is about, how it would couple to the standard model, or pretty much anything apart from that. So anything past that becomes the models of a very specific theorist who has a very specific idea in mind as to how dark matter would operate. And that's just not something I can feel comfortable talking about too much. And then we get to the one that you're probably more familiar with, baryonic matter. This is just everything in the universe. Desk in front of me, microphone in front of me, monitor or mobile phone or iPad or whatever in front of you. So there's a lot of discussion about what this could be, this regular matter that we can't see in front of us. A couple of the ideas are, primordial black holes. So black holes at the very beginning of the development of the universe that just have kind of sat there for years. We've never been able to see them form because they formed right at the get-go of the universe. And we're not able to see what they're doing because they're black holes. It's kind of tricky to do that. It's kind of the point. There's also brown dwarfs for the same reason. Very dim stars that produce pretty much no light, but still substantially heavy. It's very boring to talk about baryonic matter in this kind of talk, though, because you're not here to learn about density of black holes in the solar system. And if you are, I'm very sorry, I'm not the person to talk about in terms of that. There's other very qualified members of the AstroSoc committee who could explain that better than I can. But there's a lot more exotic physics to talk about, right? The what-ifs, the spitballing different ideas onto the wall, and eventually one of them will stick. There's also a lot of statistics to do with the baryonic matter that seems to say that if it is a dark matter candidate, if there are these primordial black holes out there, it can't really make up more than about 5% or so of the dark matter that we see. Though, again, we'll get back to that one. So how do we find dark matter? Well, one of the ways we can do this is using the Large Hadron Collider in CERN. The Large Hadron Collider is one of the highest energy particle accelerators we've ever been able to produce, currently world leading at around 13 TeV. It's capable of colliding protons together at speeds faster than ever before, which also has the potential to produce entirely new, especially heavy forms of matter in the universe. And the hope is that by being able to produce particles like this at experiments such as the ATLAS experiment, we'll be able to find these heavier forms of matter. On top of this, there's the chance of being able to use experiments like LHCb to probe, again, the CP symmetry problems that we've got, and looking in detail at the fact that there's this matter-antimatter asymmetry in a bunch of the decays we're looking at, specifically in the field of B mesons, and in the context of Na62, kaons. So hopefully by being able to probe these specific fields in more detail, we'll be able to learn more about the standard model, the problems with the standard model, and provide evidence and better constraints as to what kind of properties beyond the standard model physics would need in time to be able to produce a higher energy accelerator within the next, 10 years or so. Joking aside, I don't want to talk about the LHC too much in this talk. It's very done and tested, and there's people better qualified to talk about it, and it also doesn't really lend itself to outreach talks like this towards, the common people. There's a lot more interesting stuff out there. But what kind of stuff is out there? Here's the Earth. You're probably quite familiar with it at this point. And it's got, an atmosphere around the outside of it, and it's got a Rayleigh scattering layer around the very topmost area, and a lot of coverage. You've got, the ozone layer that's blocking a lot of stuff. And that's quite good for us because it means we don't all get cancer and die. But it's quite difficult for particle accelerators. Woe betide them. So here's the ATLAS experiment. This isn't quite to scale. And here's some matter from out in space. In this case, we've got a cosmic ray in the form of a muon. And this muon does a bunch of stuff out in space, and it has a bunch of interactions. And oh, hey, there's some dark matter here. It's produced some dark matter in some way or another that we won't go into more detail about. But this dark matter can't penetrate the atmosphere. It can't penetrate the ozone layer because of the kind of energy that it's at. So, it's gone. And with it, all of our chances of discovering some beyond the standard model physics have gone with it. And all because we try to put all of our detectors and our accelerators on ground level. You might be seeing where I'm going here. How do we solve this problem? We just start searching in space rather than searching on ground level, and we change our search to looking on a cosmological scale. But how do we do that specifically? One example that only very tenuously relates is known as the CERN Axion Solar Telescope. So the CERN Axion Solar Telescope seeks to look for axions that are actually able to penetrate the atmosphere because of how little they interact with it. And the hope is that by having a strong enough magnet inside this thing, any axions going through it will turn into X-rays, which we can then detect. If you were paying attention in the previous lecture that I did, this would be breaking dark matter into stuff that we can actually see. Over the course of its lifetime, it's had a vacuum inside of it, which has been able to test for masses of axion up to around 0.02 eV. Keep in mind that the mass of the proton is around 1 million eV. And then we've also filled it with helium to test up to around 0.4 eV. So again, we're talking about very low masses here. These are upper bounds for the potential mass of the axion. Suffice to say, it hasn't found anything yet, but fingers crossed. It's also looking for a bunch of exotic solar flares and neutrinos because, again, you can only go so far when making proposals for ludicrous amounts of money when you're offering to try and find something that may or may not even exist. But it's still, despite that, making a bunch of constraints on dark matter candidates, and it was in a couple of the plots like the ones that I showed a couple of days ago. Again, I'd really recommend you go back to that talk. I don't mean to pat myself on the back too much, but I do think it was pretty good. Can anyone vouch for me on that? Put it in the comments or something, I don't know. But anyway. Now, if you were disappointed a second ago that I didn't have a nice layer diagram of how CAST works, you're in luck right here, because here's a picture of how CAST works. You've got your big old pipe going in. You've got axions that can enter through the right-hand side, and a bunch of shielding around to stop a lot of stuff from coming in at other angles. It specifically travels straight through the magnet. Around the middle point, it goes through, 10 meters of superconducting LHC magnet, and then this travels through into a detector. As nice as it is to have a diagram for this thing, it's quite simple to describe, and I feel like I'm almost doing a disservice by explaining it in the way that I am. So I'm just going to leave this slide now in a feeling of shame. And we'll go to something that is easier for me to explain, but perhaps harder for you to understand. The alpha magnetic spectrometer. Finally here, we're going out into space. Specifically, we're going onto the side of the International Space Station here, as you can see in the picture on the right-hand side here. So the AMS experiment, or AMS, is just a collection of particle accelerator parts that we've thrown out into space. And the hope is that by putting it out there, we can detect cosmic rays as they're coming in without having to worry about the ozone layer. Specifically at the moment, we're on a sub-version of it called AMS-2. 0 and 1 seem to work pretty well, so we've decided to launch another one out there. It's been out for 1 year, and the AMS experiment in general has collected what I think is 166 billion cosmic ray events, which, to be honest, is quite small from a particle physics perspective, but at the same time, that's still a lot of data. There's some evidence of asymmetry when it comes to this experiment. The following data was found by AMS over the course of a couple of years of running AMS-1. Now, this plot shows something called rigidity, which is related to how likely a cosmic ray is to kind of be deflected off course, so how much energy you need to put in to deflect a cosmic ray, which kind of relates to mass to an extent, or at least the relation between mass and energy. And you can see on this plot that there is a weird difference between some of this kind of matter, specifically the red and the blue plot, and the green and the purple, which are for particles and antiparticles, for protons and antiprotons. Now, you would expect these two plots to behave the exact same for matter and antimatter. Again, charge symmetry. But it doesn't. And there's a couple of potential explanations for this. One of these is that they're being produced by different things in different places out in space, and this affects how they're deflected when they reach us. But at the same time, it's still an interesting little piece of data, especially when we've had so little research into antimatter in the past. Antimatter just being the opposite charge to whatever regular matter you've got out there. So there's still a chance that it could be dark matter. Let's cross our fingers and hope. Now, if you thought you were going to get away from these presentation slides without having a nice little diagram, a cross-section of the way that AMS works, you've got another thing coming. And here it is. Here's the other thing that's coming. It's a nice little cross-section of the way that AMS works. Now, this is quite a complicated diagram, I agree with you there. But in particular, I'd like to draw attention to a couple of little parts just going up the detector and how it picks up a signal from those. The first of these is the eCal, which is short for electron calorimeter. A calorimeter is just a part of a detector that can work out how much energy is being put in. So you normally put in a great big slab of lead and a bunch of circuits attached to it. A particle travels through this slab of lead, deposits a bunch of energy inside of it, and then your detector pot can say, hey, this much energy was put in. And you can combine that bit of data with a bunch of other parts from your experiment to say, hey, this thing traveled through. One of the other parts that it can use to do this is called RICH, which is short for Ring Imaging Cherenkov Detector. Cherenkov radiation is a whole other beast that will be quite difficult to explain to go into detail about it, so I'll just leave it at that Cherenkov radiation is kind of analogous to a sonic boom, but for light. In the same way, the faster a particle's going, the tighter its cone of Cherenkov radiation. And because of that, a Cherenkov detector is capable of working out how fast something's going. So you can see how you compare kind of the speed something's going at and the energy that it has, and put those two pieces of data together to work out quite a bit. After this, you've got something called the time of flight detector. Now, I talked about this a couple of days ago in my previous talk, so to keep it simple, you've got a great big chamber, you put a magnet inside of it, and you can work out a lot about the particles going through by working out how they bend when exposed to that magnet or that electric field. Finally, right at the very top, you've got the transition radiation detector, a combination of different types of silicon that are just designed to pick up those last few signals and come to a very final conclusion from the kind of impulses they receive about just what has gone through your detector. So with all that data put together, you can get a very good estimation as to what kind of cosmic rays are going through your system. Cool. But enough about particle detectors. I've used my title as a little loophole to keep on talking about particle accelerators and detector methods and whatnot. Let's talk about space. In space, you've got quite a bit of dark matter, and you've got quite a bit of regular matter, which I'll say again is called baryonic matter. Here's a muon, for example. But you've also got a lot of dark matter out there. Now, what's the one thing we know about this dark matter and this regular matter? It all has mass, so it's all dragged in and gravitationally attracted. And to an extent, the way that dark matter behaves is going to influence the way that the baryonic matter does. It's going to be pulled towards the dark matter, and the dark matter is going to be pulled towards it. So the way that this regular matter moves and operates is going to be influenced by that. Except we can't actually see the other matter, we just see the regular matter. So how can we work out from the way that the regular baryonic matter works and moves how dark matter behaves? Well, you can go and look out in space as an example, and then you can look at what you see and see how that compares to what it should look like. That's one of the ways that we found out that dark matter existed in the first place with Fritz Zwicky, and we can keep on chasing down that rabbit hole until we eventually find out what dark matter is. You can look at specific and smaller things as well. So in this example, you've got kind of the evolution of a star and how that can be influenced by the dark matter around it. And that's an interesting field in its own right. On top of that, you could just put your numbers into a computer, have a bunch of particles that you have in a little computer simulation as you start up, and see how they move when they're all attracted to each other. And from that, kind of take a stab as to what kind of dark matter is there in the background. And we're going to talk about each of these in a little bit of detail to an extent. And we're going to start with that last point, with something called a semi-analytic model. And I'm going to start this very nice video going at the same time, so you can watch kind of an example of this go as I witter away. So a semi-analytic model is any attempt to model some dark matter effects on baryonic matter, but not quite all of them, because it's quite expensive to do all of them, right? You'd have a computer working until just about the end of time. It turns out there's a lot of these semi-analytic models out there, because it's very easy to build quite a strong computer, download some kind of source code from online, and just set it ticking with a bunch of different settings. But you can still find some interesting results from them. In particular, whenever we've tried to model regular matter and dark matter together with our current predictions, we get two specific problems that are coming up. One of these is known as the satellite problem, which is that if you were to ever look at a bubble like the one that you can see here, this halo that's formed in our diagram to the right hand side, inside of that you'd find too many smaller little circles of dark matter, much more than you would actually see in reality. So either that's something that's wrong with our simulation, or it's something that's wrong with our assumptions of dark matter, or it's both. On top of that, we've also got something called the cuspy core problem, the idea that the density of this kind of structure is much more compressed into the inside than the outside, whereas in reality, from what we see, there's just as much dark matter towards the outside of galaxies as there is towards the inside. We think that quite a few of these could be related to what's called a feedback system, so the idea that everything in the universe happens at the same time, but a computer can only do one thing at a time. So you don't get the reaction to any specific action within the simulation quite as quickly as you should, and that will affect the results that come out. One of the systems that's done the best job at counteracting this is a system called Galform at the University of Durham. This has managed to place very, very heavy constraints on what should happen with warm dark matter in particular. Warm dark matter being dark matter of a low enough mass that it's affected by relativistic effects. It kind of travels near the speed of light. It specifically found that warm and hot dark matter is probably below the mass of around 2 electron volts, though it placed its constraints depending on the mass of the Milky Way, the bit that we're inside of, which we don't actually know the mass of well enough to place a tighter constraint than that. So as soon as we manage to get good measures as to how heavy our solar system is and the Milky Way, we can get better measurements of what dark matter is, and it's funny how these things work out, right? I think I would be crucified if I didn't do a couple of AstroSoc presentations without mentioning a telescope. So here's one. The Large Synoptic Survey Telescope, LSST for short. It has a 3.5 gigapixel camera to take pictures of space with, and it's got larger mirrors inside of it than any other that's been built before, and anything further than that I explain about the specifics of the telescope, and I would make people watching very, very angry. So go and listen to one of them about it. But it covers a fairly large amount of area. It's covering around 118,000 degrees squared, with a bunch of focus being placed on specific regions of interest. So a couple of the Messier objects in particular having LSST really focus on them to get as high a resolution of picture as we possibly can. It's specifically looking for weak gravitational lensing, so looking at the way that light bends in space and how that can tell us stuff about dark matter at a closer scale than ever before. It's looking for baryon oscillations in the cosmic microwave background, which is a hell of a thing to talk about, and as a result I'm not going to. And it's talking about supernova, which is something that I do feel I can talk about quite a bit. The way that stars evolve can be influenced by the dark matter mass that's around it, and that's something that we haven't really accounted for at the moment. It's also working with some direct dark matter detectors out there, such as the LZ experiment, which I should remind you is my PhD. And it's hoping to look at the distributions of dark matter in our solar system, and both how that would affect experiments like LZ and how predictions from LZ would affect our models of the solar system. So kind of both helping each other out like that. And finally, I really couldn't get away from a presentation like this without talking about gravitational waves. I think it is mandatory at AstroSoc events. I think they have it in the Constitution. I'm not going to patronize you and explain about LIGO. You're probably very familiar with it. We do a lot of talks on gravitational waves. In particular, though, LIGO is doing a very heavy search at the moment for primordial black holes. If it's heavy but we can't see it, we can see the mass waves coming in towards us. There's also the potential that axions out in space, remember those from before? The axions can clump together within the galaxy, and that these clumps would be much easier to detect if we search for their mass than they would be as individual particles. So there's a question for you. Could dark matter be entirely primordial black holes? It's unlikely. Again, we found before in the past that the upper constraint on the number of black holes out there that could make up dark matter is around 5%, but some more recent papers published around September this year, in fact, have said that a lot of the constraints related to primordial black holes might not be as valid as we thought they were, following some Monte Carlo simulations. I'll get back to you on this. I need to read up on this paper myself to be able to present it during an LZ conference, so give me a week or so and throw me an email and I might actually be able to explain that paper, or at the very least I can, send through a link to people who are interested. But yeah. Turns out gravitational waves, they're useful for just about everything, and that includes searching for dark matter. So I've ticked off the boxes that I wanted to talk about when it comes to these neat little acronyms, and as you can tell, each of them had their own different way of probing for dark matter, and they all used space in one way or another, rather than using ground-level signals. But there's a couple of conclusions to wrap up this presentation, tie everything off in a nice neat little bow, The first of these is that, as we can see, a lot of the models for dark matter might be kind of spitballing ideas, nothing that's really substantiated, but they would all prove to be very neat and tidy solutions to the standard model, solving a lot of problems that have been out there for quite a while. We should also add that there's a lot of dark matter in space. 25% of stuff is dark matter, 80% is dark energy. So we can either watch this huge amount of stuff come to us, or we can go out to it, view it from a distance, model it from a distance, and see how this kind of compares to what we would expect with our current theories, much like how ground level particle physics will compare the way that stuff decays to what we predict. It turns out physics is a huge amount of making measurements and comparing them to theory, who would have thought? But both of these methods can help us make very nice constraints on what dark matter could potentially be, and both of them are both useful in their own individual way and can really help each other. So in a way, astrophysicists and particle physicists, we kind of need each other. But with that being said, thank you so much for listening. I can't believe you managed to make it through another 40 minutes of me whittering on about nothing. I've left a little picture of the LZ experiment itself here, just as a nice little reminder to me of what I've got to look forward to at some point. And what you could too if you work for the LZ experiment at some point. I'm still trying to recruit here. With that being said, there may or may not be a Q&A session happening after this, depending on how busy I am next week, which for you is right now. And if I'm not about, I'd be happy to answer any emails. Even if I am about, just throw me an email about what a dark matter is. I'm happy to answer. I've got nothing better to do at the moment. Most of my life is watching Zoom calls. So send a message through, and I hope you've been able to take something away from this. It's been an honor to do a bunch more lectures for AstroSoc, and I hope you'll have me back in the future, even if the only thing that I'm really qualified to talk about is dark matter. But with that being said, yeah. Thank you very much, and have a nice day.